we are still on this page. This is the section where suddenly we have these major ideas in statistics: standard error, confidence interval, residual standard error. Now, if we go back to the code that we had in our previous session, this is where we started with a predetermined relationship. These are the examples where we say we're omnipotent. We know the true relationship between the predictor variable and what we're trying to predict. And I've taken a gradient of 5, or is it an intercept of 5? An intercept of 5 and a gradient of 2. We have our random error, our epsilon term, with mean 0 and standard deviation 3. Now, what I've done, which is slightly different to, I've just edited the code that we finished off with last time, is in this loop, which we use to calculate each beta, for each beta 1, the slope parameter, the gradient, for our different data sets. Just remember what we had done last time. We said, let's look at 50 different data sets, each data set with 100 observations, but no two data sets are likely to coincide, so they have their own different biases, and it's those biases that have us speaking of standard error in the first place. We're never looking at the full population. Very often it's impossible, even if there are situations where, if you'd like to estimate the mean height, which is an example we seem to be taking quite often these past few sessions, you could, in theory, interview or measure. You're interested in a specific group of individuals, pilots, astronauts. Even if in those cases, I suppose you could interview each individual, there are many other situations where you can't quite. It's a bit more abstract. If it's insurance and it's an insurance claim, or if it's stock prices and you're looking at movements, even if you have the full extent of data these past 100 years, there might be events the following day after you've created your model, after you've made your predictions, that are in no way that don't have any of the features that would have been present in the data used to model. And what have I changed? I've changed one thing. And looking back at our previous meeting, probably been a good idea had I done this. What I'm telling R, it's really simple. Didn't we have the plot of these 5,000 observations? But then we partitioned them, we parceled them off into 50 separate data sets of these 100 observations. What I'm doing over here is I'm telling R to plot only the first 100 observations, then the next 100, then the next 100, then the next 100. So if I run this, it's actually plotted each data set. This is the last data set. This is the 50th data set. Over here, we could make this larger. This is the 50th data set, and we can go back. This is the 49th, etc., etc. These are all the different data sets. Now, you would imagine they are roughly in line with each other. They roughly exhibit the same features. And which features are those? Well, theoretically, these are the two parameters that we should be able to see over here. So roughly a gradient of, keep on modeling these up, a y-intercept of 5 and a gradient of 2. But there will be deviations between one data set and another. I'm trying to stress the following over here, that in practice, you will only have one data set. You might have this data set. I'm looking at the first one. What our calculations need to exhibit is that this data set isn't telling the whole story. Who knows? Maybe we, on another day, circumstances would have had it that we would have collected this data. We're still looking at the same variables, but who knows? Maybe instead of interviewing people, if the data subjects are people between 9 o'clock and 10 o'clock, I don't know, we woke up later and we interviewed people between 10 o'clock and 11 o'clock. And that might result, especially the smaller your sample is, in differences between what you may have collected against what you have actually collected. Each of these data sets, now in practice, you will only have one. This is important. In practice, you will only have one. But each of these data sets will give you different parameters. Now, the differences might not be that large, but that's what we're trying to measure. What does even not that large mean? Well, not much, not much. So let's go back to our original code. I'm going to put a hash over there to comment it out. That's how you get R to ignore any code. Really useful if maybe you don't want to delete a line of code, although you wouldn't want to use it. Also really helpful for including comments, especially if you want someone to check your work, or you just want to increase your chances that if you come back in a month's time, perhaps we've all been in this situation, maybe in an Excel file, maybe just studying for an exam, and you have a calculation that you remember understanding it when you would have originally performed it, but if enough time passes by, then you're not entirely sure what you would have, what the logic behind it is. So this is where in R, and it's actually considered good practice that every few lines of code are punctuated with comments. Although I'm not using it for comments, I've just done it to remove this line of code. And let's run the whole thing. And running the whole thing does what? It's given us this summary for each beta 1. Beta 1 is the slope. We've calculated 50 betas. You can see them over here. There's a way to remove the name. I think it's unname. Unname, perhaps. Hopefully this works. Yep. And each of those values is a different beta corresponding to a different data set. Now, theoretically, the formula to measure sort of the extent of the variation within your beta 1 up to 95% confidence is this one. How is this calculated? This is calculated using this formula, but you need to square root it. And I really think this is probably, we've said enough on this topic, and hopefully we better understand what we mean by beta 1 hat and plus or minus 2 times the standard error in beta 1 hat. Now, hypothesis testing. This is where you're going to go beyond your beta 1 hat, which is a point estimate. And we need to ask ourselves, is the relationship between x and y? Now, just because your beta 1 hat isn't exactly 0, and it will hardly ever be exactly 0, doesn't mean that we should simply conclude that there is a relationship. Remember, beta 1 is the slope. If it's not 0, then there is some kind of relationship. Possibly negative, possibly positive. We need to look at our beta 1 hat and ask ourselves, how confident are we that the true beta 1 is non-zero? So we have an estimate. We have our beta 1 hat estimate. That gives you the slope. We're setting up a hypothesis test where we need to answer the question, how confident are we that the true beta 1, the true slope, is not 0? And there's a standard test, which is what maybe we'll try and discuss today. And it's called, or it's based on what we refer to as a t-statistic. Now, this entire book is on statistics, statistical learning. Let's just remind ourselves what we mean by a statistic. A statistic is typically a single value. And this single value attempts to describe the data. Specifically over here, the t-statistic, once my cursor emerges, here we go, this t-statistic is calculated as follows. Take your beta 1 estimate and see what its distance is from 0. This is the null hypothesis. The null hypothesis is that there is no relationship. This is the innocent until proven guilty. And then you're going to divide by the standard error in the beta 1 hat. Now, to my knowledge, the way hypothesis testing works, and it's been a while, we're going to feed this, once we have the value of t, and for example, it's 17.67 for the slope, TV means the slope. It's television. There are two. We can probably find this in the earlier pages. Here we go. Here you go. You have your intercept parameter, and you refer to this as your TV parameter. And we're regressing units of sales onto the TV advertising budget. It's different units, right? Sales is how many, maybe thousands or 10,000s of units you're selling. Think of microwaves, think of you name it, you name it. Hotel bookings. TV is measured in, it's going to be a monetary value, dollars, euros. And we're performing a test on either parameter, on both parameters. And the test is as follows. We've estimated our beta naught hat, estimated our beta naught hat. Its standard error, dividing these two, gives the t statistic. Gives the t statistic. It's that formula that we've just discussed. And then you calculate the probability. The what probability? Let's see how these things work. I think we would need, let's see. It's actually quite simple, but I realize we're not necessarily. Let me see how the book does it so that we don't. Let me give you the punchline. This p-value, that's a probability. That's a probability. The smaller it is, the more likely you are to reject the hypothesis. And every hypothesis test works this way. You calculate a p-value, and the smaller it is, and then you normally set a threshold. For example, the book is speaking of 5% or 1%. Think of this as the smaller your threshold, the book refers to it as a cutoff, at least over here. The smaller the cutoff, the stricter you're being. So think of innocent until proven guilty. You can, there's a difference between civil court and criminal court. If it's a criminal case, it needs to be, the phrase is beyond a reasonable doubt. Well, what do we mean by reasonable doubt? Whereas in civil cases, it depends on the jurisdiction. It depends on the handbooks that judges and magistrates are required to follow when, or jurors as well, I would imagine, when handing down a sentence. Well, for example, beyond a reasonable doubt might be, for example, you're in the 90% confidence interval. You need to be 90% or higher to convict someone and to consider them guilty as opposed to innocent. If it's a civil court, to my knowledge, I think it might just even be, if it's greater than 50%, then that's guilty. It really depends. It really depends. And it's going to vary from or between jurisdictions. But the idea is this. The idea is this. When you come to, where is my cursor today? When you come to reject or accept, you never accept, by the way, and I'll get into that very soon. When you come to reject the hypothesis, you need to be within a certain level of confidence. And the way it works is as follows. The smaller this value, and we'll see if we can manage to calculate it, the smaller this value, if you're, for example, if you have a cutoff of 5%, if the p-value is less than 5%, then you reject the hypothesis. So you would reject that there is no relationship, and you're sort of implicitly saying that instead you're going to take the alternative hypothesis. But you never speak of accepting the alternative hypothesis. We're a bit more conservative in even just the way we phrase things. Instead, we speak of rejecting the hypothesis or not rejecting the not even rejecting the hypothesis and saying there is not enough evidence to reject the hypothesis. But over here we reject, and I did say we would try calculating this value. Let's go into R. Not promising anything, but would we have to say T? Would it just be R? Let's see if we do RT. TT is the T distribution. And that hasn't worked. You need to give the degrees of freedom. All right. We don't know the degrees of freedom, do we? The degrees of freedom don't let it's the parameter every, and I realize I'm sort of jumping from one idea to another over here. Let's do it this way. Let's do it this way. So, for example, there are many different probability distributions. We've really discussed three in these sessions. There is the normal distribution, that's the bell curve. There is the uniform distribution, where every outcome is equally likely. There is the binomial distribution, where think of it as either heads or, yeah, you can, for all intents and purposes, think of it as either heads or tails, either 0 or 1. But these are families of probability distributions. So, for example, the normal distribution, over here, I chose a mean of 0 and a standard deviation of 3. I could take different means and standard deviations, and each one gives me a different member, a different element of the family of normal distributions. It's the same thing. It's the same thing with the T distribution. And the T distribution requires that you specify the degrees of freedom. It's not something we're really going to go into today. So not entirely something I remember either. But if I just call these T values, give you an idea of what the T distribution looks like. And it might remind you of the normal distribution. In fact, the higher the degree of freedom, or at least this is how I remember it. Well, might be one of those things. Fact check me on it, or I'll double check once we finish today's session. The higher the degrees of freedom, the closer we get to a normal distribution. So there is a concept where just like at A level, we discuss sequences that converge to a specific value, possibly the best known one, and it's used in finance as well, as the geometric series, where if you keep on adding, that series converges to a specific sum, and you can speak of the sum to infinity. It's the same situation with certain probability distributions, that if you, for instance, in this case, keep increasing the degree of freedom, the closer it resembles, or the closer it gets to resembling a normal distribution. Now, can we do the following? Can we ask, and let me just think about this for a second. What I would like to discuss, so that you get an idea of how hypothesis testing is performed. What I would like to see is, for example, how do you check? So what's the book saying? The book is saying, if we have, I think this would be maybe the degrees of freedom. If we have 30 degrees of freedom, two, the values generated are 95% of them, I've just deducted 5, 95% of them are going to be less than 2. Let's have a look. So what do I need to ask? What if I do t values, and there's probably an easier way, less than 2? Look, this is one way. It's a long way. It's a long way of doing it. But you see all these trues? Some of them are false. So you could actually count the number of trues and divide by 10,000. Let's see. How would I actually do this? Could I say, I'd like to count. I'd like to count how many of these are less than 2. And how do we do that? How do we do that? We have t values. Now you could do something with a double equals, to my knowledge, but let's go back to this. So all those values that are less than 2, could you save this as a vector? Like if I call it vector z? Yes, apparently you can. So could I now just do sum of z? Because I think what R does is true takes a value of 1. And yeah, look. And false takes a value of 0. Like I said, there's probably a much easier way of doing this, but we've kind of hacked it in order to use the sum function to actually count the number of these values that are less than 2. Now, in fact, what you'll notice is that we don't get 5, but we don't get 95%. We get 97.5%, because you know what? I think what I had to say was t values is, think of the absolute value is greater than, okay, now that doesn't work. What if that doesn't work either. Can we use maybe an and? Well, you know what I could do? I could do absolute value. Now that's interesting. Or is it because I need to remove this parentheses? Okay, this seems to have worked. And look at that. So that worked. We are practically in perfect agreement with the book. What is the book saying? Let's look at the book. The book is saying when n is 3, this probability cutoff, 5%, corresponds to a t statistic of around 2. Now, what does that mean? What does that mean? Let's take this 5%. Let's take the 5%. What it's saying is the following, that theoretically, and we've taken 10,000 to get us, to hopefully get us close to the theoretical value. 95% of the generated values shall be between -2 and 2. Like this. That's 95% of your values. 95% of your values. If something follows a t distribution with 30 degrees of freedom, it's not that important what the 30 degrees of freedom means for the time being. You should only expect theoretically 2.5% of your values to be less than -2, and 2% of your 2.5% of your values to be greater than 2. Meaning what? Meaning what? That to reject the null hypothesis, your t statistic, I'll use, well, we're rejecting, right? So shall I use red for rejecting? Your t statistic has to be somewhere here or somewhere here. It's probably easier to just work with the absolute value, right? If we spoke of the absolute value, we could ignore half. We could ignore half of this diagram and just look at those values greater than 0. I am inclined on doing it that way, removing all of this and just speaking of the absolute value. So you calculate your t statistic, take its absolute value. So if it's negative, drop the negative. If it's positive, just keep it positive. You reject the hypothesis. You reject the hypothesis if your t statistic is greater than 2. Now, one second, but is this the criminal case where it's beyond the reasonable doubt? Is it a civil case where you simply need greater than 50% likelihood that an individual is guilty? This is at the 95% confidence interval. So I'll use orange, and at the 95% confidence interval, at the 95% confidence interval. So although the book is sort of speaking of a 5% cutoff, but it's the same thing. At the 5% cutoff, any t-value, no, excuse me, any t-statistic greater than 2 leads us to reject the null hypothesis. So if you are until 2, you are 95% confident that the null hypothesis should I say reflects reality? I'll just say that the data suggests or indicates that we have the null hypothesis. Beyond that, you reject the null hypothesis. And that's probably the best I can do over here. So we have this t-statistic of 15.36, significantly larger than 2. And this t-statistic of 17.67, again, significantly larger than 2, which is why the p-value is less than, that looks like 0.01%, right? So much, much smaller than 5 or 1%. Let's see. Table 3.1 provides details of the least squares model for the regression of number of units sold on TV advertising budget for the advertising data. Notice that the coefficients for beta naught hat and beta 1 hat are very large relative to their standard errors. This is what we're comparing. We're comparing the estimate against its standard error. The larger the numerator is relative to its denominator, the larger the t statistic is, and the more likely you are to reject the null hypothesis. The probabilities of seeing such values if h naught is true are virtually 0. Hence, we can conclude, and we're rejecting h naught over here, hence we can conclude that beta naught is not equal to 0, and beta 1 is not equal to 0. So that's the very first time that we've performed a hypothesis test. The one interesting thing would be how to actually calculate this t-statistic. No, beg your pardon. We know how to calculate the t-statistic. That's 7.0325 divided by the standard error. It's actually how to calculate this probability. And I wonder if we can do this. How would this work? How would this work? Well, we need to use, instead of RT, I think we need to use like DT. Let's see. Okay, this is perfect. This is perfect. Look. DT, PT, QT, and RT. So what does each one do over here? What does each one do over here? So P is the vector of probabilities. No, that's not what I want. N is the number of observations. DF is the degrees of freedom. Q is the vector of quantile. Well, why don't we try each one and see? Let's try DT. We could always look at the documentation. And if I give it the books 15, if I give it the books 15.36, and we say degrees of freedom 30. Yeah, that might be it. That might be it. That might be it. Let's see what Q does. Yeah. So why don't we give it 2? So if the P or was it the D? If the D does what I think it does, when I run this line of code, it should give me 97.5%. Ah, okay, but it's giving me the complement of 97.5%. No, not quite right, because I said, let's try P. Okay, so I think it's P. What P is doing is it's asking, what is the probability of getting a 2? It's the cumulative, what do we call it? The cumulative, the CDF, the cumulative. This is going to Wikipedia. CDF probability. Yeah, the cumulative distribution function. Exactly. Is there like a really simple example over here? By the way, we're looking at the same website. We're looking at the same page over here as when we did that session on Excel when we had met up. Yeah, yeah, exactly. So what we're doing is this is our distribution function, and we're going to set the cutoff at 5%, and the probability that your value that the values that a randomly selected value is less than 2, is less than or equal to 2, strictly speaking, is or you calculate as PT. P is whenever you could have it for the normal distribution function. You could say P norm, and you could tell it, for example, 0. And let's do it a standard normal distribution. 0 mean and standard deviation 1. This should come to exactly 50%. Yeah, 0.5. For the simple reason that if it's a standard normal distribution, you have a 50% chance of getting a positive value and a 50% chance that you get a negative value. Okay. So I think we've calculated this. The p-value is less than 0.001 because when we give it 15.36, when we give it 15.36, you get 1. Right. Should I be doing 1 minus? Should I be doing 1 minus? Yes. Okay. Isn't this what we had earlier? Yeah, close enough. Close enough. I'll have to double check. Like I said, the documentation, there is DT, PT, QT, and RT. You would think that I know how to distinguish between them, but I don't know them offhand. I don't know them offhand. I know RT because RT is to generate just a random observation following the T distribution. Okay, I think we can safely say that we've probably invested enough time into hypothesis testing, and we have around like 15 minutes left. We started slightly later than usual. I wonder if I should just skip this section. We started it last time, and I didn't really feel it was getting us anywhere interesting. We'll have to do it at some point. These are fundamental ideas. But it might be a good idea to move on to multiple linear regression. We've spent so many sessions now, easily, I would say a week now of meetings, speaking of simple linear regression and getting into the details, performing calculations. We even looked at how you would calculate the standard error without the formula of the standard error, assuming that you had enough data sets. Although, like I said, in real life, you will always have one data set. That it's probably time to move on to extending these ideas to multi-dimensional modeling. So let's have a look. Simple linear regression is a useful approach for predicting a response on the basis of a single predictor variable, what we've been labeling as X. However, in practice, we often have more than one predictor. For example, in the advertising data, we have examined the relationship between sales and TV advertising. We also have data for the amount of money spent advertising on the radio and in newspapers. And we may want to know whether either of these two media is associated with sales. How can we extend our analysis of the advertising data in order to accommodate these two additional predictors? Additional predictors being the radio budget and the newspaper budget or expenditure. One option is to run 3 separate linear regressions, each of which uses a different advertising medium as a predictor. For instance, we can fit a simple linear regression to predict sales on the basis of the amount spent on radio advertisements. Results are shown in table 3.3. So over here, we're regressing sales on radio, and you have your intercept term and your slope term, as well as on newspaper budget. Notice just to keep things in context, the TV slope, we estimated it as 0.05, and it's a lot lower than the radio and similar to newspapers. So it would appear that you're more able to influence the sales using the radio advertising. Let's see. We find that 1,000 increase in spending on radio advertising is associated with an increase in sales of around 203 units. That's the slope. And for newspaper, a $1,000 increase in newspaper advertising budget is associated with an increase in sales by approximately 55 units. Okay. However, the approach of fitting a simple linear regression model for each predictor is not entirely satisfactory. First of all, it is unclear how to make a simple prediction of sales given levels of the 3 advertising media budgets, since each of the budgets is associated with a separate regression equation. Secondly, each of the 3 regression equations ignores the other 2 media, informing estimates for the regression coefficients. We will see shortly that if the media budgets are correlated with each other in the 200 markets, these are just the 200 data points of the individual, no, in the 200 markets that constitute our data set, then this can lead to very misleading estimates of the individual media effects on sales. Right. So what's going on over here? Well, I think we had a diagram at one point with all three of them. May have been in the previous chapter. These. And the thing is, modeling them separately, you don't actually know if the sales data isn't really being driven by the TV, but it's actually being driven by the radio. Remember that these observations, for example, let's look at this one. This is the same as this, is the same as this. That's the same data subject. So if we're looking at marketing over here, if we're looking at advertising, think of that as, for example, I don't know, in Italy. What your database would actually have is it would have a single row, but 4 columns. TV, the TV budget, the radio budget, the newspaper budget, and the sales. So in actual fact, let's say you have 50, 80, and 20, and sales are 2, right? So sales look like around 2 over here. Do you in fact know what impact the TV budget had on the 2,000 units sold? What impact the $80,000 had on the 2 units, or on the 2,000 units sold, and what the $20,000 had? There is this question, isn't there? There is this question: what's actually driving the sales? So, for example, to take this, that's the same data subject. If that's Germany, that's the same data subject in each one. It's the same level of sales in Germany, but you're looking at what you spent on TV in Germany, on radio in Germany, and on newspapers in Germany. So you need to watch out. These TV, radio, newspaper, they might be interacting with each other is the word. So let's continue to see what the book has to say on the subject. And we were over here. Instead of fitting a separate simple linear regression model for each predictor, a better approach is to extend the simple linear regression model so that it can directly accommodate multiple predictors. We can do this by giving each predictor a separate slope coefficient in a single model. In general, suppose that we have p distinct predictors. So, for example, 3 of them: TV, radio, and newspapers. Then the multiple linear regression model takes this form. So now we now have additional we don't have till beta 1. We also have beta 2 until beta p, where xj represents the jth predictor, and beta j quantifies the association between that variable and the response. We interpret beta j as the average effect on y of a 1 unit increase in xj, holding all other predictors fixed. Those of you who've just started partial differentiation, it is exactly the same concept, isn't it? You are holding all the variables fixed. You're not varying them, but you're only looking at how the output changes when you change one of the variables. The effect, the rate of change. So you could even start thinking of, for example, the partial derivative of sales, partial sales by partial radio. Everything else is fixed. Estimating the regression coefficients. So these ideas will now, everything that we discussed earlier will now manifest itself over here. As was the case in the simple linear regression setting, the regression coefficients beta naught until beta p are unknown and must be estimated. Given estimates beta naught hat until beta p hat, we can make predictions. So if you've estimated these, if you have some kind of estimate, you can now estimate y depending on x1, x2 until xp. Notice no error term, because the error term has a mean of 0. So this is your expectation, what you expect. Naturally, then you normally set a confidence interval to give an idea of the uncertainty within your expectation. So I expect Moldova to receive so many points in the Eurovision, or to place to rank in this position, fourth, but with a margin of error, with a confidence interval. So I don't know, but I'm 95% confidence that Moldova will place in the top 6. So it's no longer a point estimate, but you've created an interval now. It's third position, roughly plus or minus 2 positions higher or lower. Maybe I should have said top 5, but you get the idea. Notice there's no hat on x1, x2. That's typically what you know, right? So if I intend to spend so much on TV, then you know it. You know your budget is for next year's marketing cycle, $10,000 on TV, so much on radio, so much on newspapers. The parameters are estimated using the same least squares approach that we saw in the context of simple linear regression. We choose a beta naught hat value for beta naught, a beta 1 hat value for beta 1, until a beta p hat value for beta p, to minimize the sum of squared residuals. This is based on your training data. Your training data for your n observations, and I think in this advertising data set we have 200 of them. You know the sales output for each observation. You estimate you estimate negative y hat using this. And if you add the green and the blue and square so that it's not negative and add everything, that is your residual sum of squares. The residual is just the difference between your actual and your predicted, your actual and your expected. And this is what we create. This is what we create. This is with two predictors. It's linear regression. You're expecting a linear object, aren't you? So if it's in 3 dimensions, we now have a plane. Notice that, let's use color black, for instance. Notice that each black arrow is y minus y hat. Your actual minus your predicted. What you want to do is you want to minimize not one particular black length, not specifically this one, not specifically this one. You want to minimize the sum of all these black lengths squared. The sum, yeah, the sum, maybe the sum of the square of these black lengths. And that's exactly it. We'll maybe read this last paragraph. The values beta naught hat until beta p hat that minimize 3.22, that's simply this over here, or the multiple least squares regression coefficient estimates. Now, unlike the simple linear regression estimates, the multiple regression coefficient estimates have somewhat complicated forms that are most easily represented using matrix algebra. So they were very easy, weren't they? Over here, it was just, may have skipped them. It was just these two formulae. And over here, we didn't use partial derivatives. We used exact derivatives, d by, no, actually, I think even over here, we were using partial derivatives, right? We had beta naught, and the RSS is a function of 2. So even in simple linear regression, you still have multiple parameters to estimate. You have your intercept parameter and your slope parameter. Figure 3.4 illustrates an example of the least squares fit to a toy dataset with p equals to predictors, which is these two over here, x1 and x2. Now I can make, once I have the plane, now I can make predictions, right? If I have a specific x1 and a specific so for example, if my x1 is 50 and my x2 is 100, those are my inputs, and I can very easily, just by looking at the plane, ask, okay, what is the output of 50 and 100? It's just going to be the height of this orange arrow. Of course, you only have a plane if it's 2 predictor variables. Very often we're going to have more than that. This is probably a good place to stop. Yep, very good. Let me just stop recording.